Tonight, we are exploring one of the most fundamental questions in all of science and philosophy. What is time? It seems like a simple question at first. Time is something you live inside every moment of your life. You feel it passing. You watch clocks mark it. You remember the past and anticipate the future. Time shapes every experience you have ever had. And yet, when physicists, philosophers, and mathematicians look closely at time, something remarkable happens. The closer you examine it, the stranger it becomes. The more precisely you try to define it, the more it resists definition. Some of the greatest minds in human history have spent their careers studying time and come away with more questions than answers. This is Sleepy Time Universe, where we explore the universe slowly and without rush. Tonight, we will move through those questions slowly and carefully. We will begin with how ancient thinkers first wrestled with the nature of time, and follow that thread through Isaac Newton's idea of absolute time, through Albert Einstein's discovery that time is flexible and personal, through what gravity does to clocks, and through the deep question of why time seems to move in only one direction. We will consider what quantum mechanics says about time at the smallest scales, whether the present moment is physically real, and what physicists mean when they say time may have had a beginning. And we will sit with the question that has troubled philosophers for centuries. Does time actually exist? Or is it something that only appears to exist from the inside of a conscious mind? Get comfortable. There is no rush here. We will take each idea slowly, give it room to settle, and move forward only when it feels ready. Let's begin. Chapter 1. What we mean when we say time. If you ask someone what time is, the most common response is to point at a clock. And that answer, while understandable, tells us almost nothing about the nature of time itself. A clock does not contain time. It does not produce time. It simply marks it, the way a ruler marks distance without containing space inside it. Clocks are tools we built to track something we noticed, but never fully understood. So let us start somewhere simpler. Let us start with the experience. You wake up in the morning and the day is ahead of you. You move through it hour by hour. Things happen in sequence. You eat breakfast before lunch. You make a phone call and then end it. You begin a task, work through it, and finish it. There is always a before and an after. There is always a direction. Events do not happen in random order. Causes come before effects. The arrow always points the same way. This is what we mean, in the most basic sense, when we talk about time. We mean that things happen in sequence. We mean that the universe has a direction, a flow from one state to the next. We mean that the past is fixed and cannot be changed, while the future is open and has not yet arrived. That seems obvious, but notice how quickly it starts to raise questions. What exactly is the past? It no longer exists in any physical sense. You cannot point to it. You cannot visit it. It is gone. And yet it somehow still shapes the present. The things that happened yesterday change the state of the world today. The past is absent, and yet it is everywhere. And the future? It also does not exist yet. It has not arrived. And yet you can think about it, plan for it, feel anxious about it. You can imagine events that have not happened. The future is absent, and yet it occupies an enormous amount of human mental life, which leaves only the present, the now, the single moment in which everything is actually happening. And here is where things get interesting. If you try to pin down the present moment, to define exactly how long it lasts, you run into trouble. Is the present a second long? A millisecond? A billionth of a second? Every time you try to identify the present, it has already slipped into the past. The now seems to have no duration at all. It is a boundary, not a container. The philosopher Augustine of Hippo, writing in the 4th century, captured this problem with remarkable clarity. He wrote that he knew perfectly well what time was until someone asked him to explain it. That observation has stayed relevant for over 1500 years, which tells you something about how difficult the problem really is. Part of the difficulty is that time is not something we observe from the outside. We are inside it. We are made of it, in a sense. Every physical process in our bodies, every thought we have, every observation we make, takes place within time. There is no vantage point outside of time from which we could look at it clearly and describe what we see. We are like fish trying to study water. Language does not help very much either. Almost every word we use to describe time borrows from the language of space or movement. Time passes, time flows. We move through time. The future lies ahead. The past is behind us. We look forward to things. We look back on memories. All of these phrases treat time as if it were a kind of road we are traveling along, or a river carrying us downstream. But is that accurate? Is time actually like a river? Rivers have water in them. Rivers exist in space. You can stand on a riverbank and watch the water go by. You cannot stand outside of time and watch it go by. The river metaphor is useful and intuitive, but it may be deeply misleading about what time actually is. This is one of the first lessons that comes from taking the question seriously. The concepts we use to think about time were built from everyday experience, and everyday experience may not be a reliable guide to the true nature of something this fundamental. Consider measurement. We measure time in seconds, minutes, hours, days, years. These units feel natural and obvious, but where do they come from? The day comes from the rotation of the Earth. The year comes from the Earth's orbit around the Sun. The month comes from the cycle of the Moon. Even the second, which feels like a fundamental unit, was originally defined as a fraction of the day. Our units of time are all tied to the motion of objects in space. This raises a subtle question. Is time something independent of those motions? Something that would exist and flow even if there were no planets orbiting stars, no moons circling planets, no clocks ticking anywhere in the universe? Or is time inseparable from change and motion? Is time what we call the fact that things move and change, rather than something separate that those changes take place inside? These two views have been debated for a very long time. One view says that time is a kind of container, a background against which events unfold, something that would exist even in a completely empty universe with nothing in it at all. The other view says that time is relational, that it only exists because things change relative to each other, and that in a universe with no change at all, there would be no time. Isaac Newton held the first view firmly. He believed in what he called absolute time, a mathematical time that flows uniformly everywhere in the universe, independent of any external thing. In Newton's picture, the universe is like a stage, and time is the backdrop against which all events play out. Whether anything is happening on the stage or not, the backdrop exists. Time flows, whether or not anything is moving through it. Gottfried Wilhelm Leibniz, Newton's contemporary and rival, held the second view. For Leibniz, time was nothing more than the order of events. It was a way of describing the sequence in which things happened relative to each other. Without events, without change, there would be no time. Time was not a thing in itself. It was a relationship. This debate between Newton and Leibniz was never fully resolved in their lifetimes, and in a sense, it is still alive today, though the terms have changed considerably. What Einstein did, more than 2 centuries later, was not simply to pick a side in that old debate, but to transform the question entirely. He showed that time and space are not separate things at all, but aspects of a single unified structure, and that this structure is shaped by the matter and energy within it. But we will come to Einstein in a later chapter. For now, it is enough to sit with this opening observation. Time is something we experience constantly and intimately, something we have built entire civilizations around measuring and managing, and yet something we cannot fully define, cannot observe from the outside, and cannot even agree on whether it is a fundamental feature of the universe or something more like a useful concept we invented to make sense of change. That is a strange place to find ourselves with something so familiar, and it is exactly the right place to begin. Chapter 2. The Ancient Question. Long before anyone had a clock on their wall or a watch on their wrist, human beings were thinking carefully about time. They had to. The rhythms of time governed everything in their lives: when to plant crops and when to harvest them, when the rains would come and when the dry season would follow, when the stars would return to certain positions in the sky. Time was not an abstract philosophical puzzle for early civilizations. It was a practical matter of survival. And yet, even in those early cultures, alongside the practical counting of days and seasons, there were thinkers who looked at time and asked the deeper question, not just how to measure it, but what it actually was, where it came from, whether it had always existed or had a beginning, whether it would go on forever or come to an end. These questions appear in some of the oldest written texts we have. Ancient Mesopotamian and Egyptian cultures developed sophisticated calendar systems and had rich mythological frameworks for understanding time. In many of these frameworks, time was cyclical. It moved in circles, repeating patterns, returning to where it had started. The seasons cycled, the stars returned, the flooding of the Nile came each year. Cyclical time felt natural because the world itself seemed to move in cycles. This is a fundamentally different picture of time from the one most of us carry today. We tend to think of time as linear, moving in a straight line from a fixed past through the present toward an open future. But for many ancient cultures, time was more like a wheel than an arrow. Events did not just happen once and disappear. They returned in new forms, echoing patterns that had repeated since the beginning of the world. The ancient Greeks brought a new level of philosophical precision to the question, and among Greek thinkers, 2 names stand out as particularly important for how they shaped the long history of thinking about time. The first is Heraclitus, who lived in the 6th and 5th centuries before the Common Era. Heraclitus is famous for the observation that you cannot step into the same river twice. The river looks the same, has the same name, occupies the same banks, but the water flowing through it is always different water. The river is in constant flux, and Heraclitus believed that everything in the universe was like that river. Constant change was the fundamental nature of reality. Nothing was truly stable. Everything was always becoming something else. For Heraclitus, time was deeply connected to this constant flow of change. Time was not a backdrop. It was the very process of change itself, the becoming, the flowing, the transformation of one state into another. To exist in time was to be caught up in that endless river of change, always moving, never fully arriving anywhere stable. The second Greek thinker who shaped the early history of thinking about time was Parmenides, a near contemporary of Heraclitus, and Parmenides arrived at almost exactly the opposite conclusion. Where Heraclitus saw change everywhere, Parmenides argued that change was an illusion. True reality, he said, was eternal, unchanging, and unified. The world of appearances, the world we experience through our senses, with all its motion and change and variety, was not truly real. It was a kind of shadow cast by the deeper reality, which was timeless and still. This idea that true reality might be timeless, that time and change might belong only to the surface level of things and not to their deepest nature, is one that would echo through philosophy and physics for thousands of years. It is, in a sense, still alive today in certain interpretations of modern physics, as we will see in later chapters. Aristotle, writing in the 4th century before the Common Era, tried to develop a more systematic account of time that navigated between these extremes. For Aristotle, time was closely connected to motion and change, but it was not identical to them. Time, he argued, was the measure of motion with respect to before and after. It was the way we counted and ordered the changes we observed in the world around us. This definition is subtle and worth sitting with for a moment. Aristotle was not saying that time is the same thing as motion. Different motions can be faster or slower, can take more or less time. Time is what allows us to compare those motions, to say that one took longer than another, that one happened before another. Time is the framework within which motions are ordered and measured. Aristotle also raised a question that has puzzled people ever since. He asked whether time could exist without a mind to perceive it. If there were no conscious beings anywhere in the universe, no one counting, no one measuring, no one noticing the sequence of events, would time still exist? Or is time something that requires a perceiver? Is it something that happens in the world, or something that happens in the mind? He did not fully resolve this question, and neither has anyone else since. But the fact that Aristotle was asking it more than 2,000 years ago shows how deep and persistent the puzzle is. Several centuries after Aristotle, a thinker named Augustine of Hippo returned to the question of time with extraordinary depth and honesty. Augustine was a theologian and philosopher, writing in the 4th and 5th centuries of the Common Era, and his reflections on time, contained in his autobiographical work known as the Confessions, remain among the most searching and beautiful ever written. Augustine began from a simple and striking observation. The past no longer exists, the future does not yet exist, and the present, the moment of now, has no duration. Every time you try to identify the present, it has already slipped away. So where does time actually exist? His answer was unexpected. Time, Augustine suggested, exists in the mind. The past exists as memory. The future exists as anticipation or expectation. And the present exists as attention, the direct awareness of what is happening right now. Time, in Augustine's view, is fundamentally a mental phenomenon. It is not something out in the world, ticking away independently of conscious experience. It is something that consciousness creates, or at least something that can only be grasped by a mind capable of holding past, present, and future together in a single act of awareness. This is a remarkable idea, and one that resonates strongly with certain aspects of modern neuroscience and philosophy of mind, as we will explore later in this video. The brain, it turns out, does not simply receive time passively. It actively constructs the experience of time from a continuous stream of information. Our sense of duration, of sequence, of the flow of moments, is something our nervous systems produce, not simply something we observe. Augustine was also deeply concerned with the question of what existed before time began. If God created the universe, what was God doing before the creation? Augustine's answer was careful and interesting. He suggested that the question was malformed. Before the creation, there was no before. Time itself was part of creation. There was no time before time began. This idea that time might have had a beginning, and that the question of what came before that beginning might not have a meaningful answer, turns out to be remarkably close to what modern cosmology suggests about the origin of the universe. Moving forward several centuries, the great Islamic philosopher and physician Avicenna, writing in the 10th and 11th centuries, developed his own careful analysis of time, drawing on Aristotle but pushing the ideas further. Avicenna distinguished between time as it exists in the world, as the measure of change in physical things, and time as it is grasped by the mind. He also explored the relationship between time and existence, asking what it means for something to exist in time as opposed to existing timelessly or eternally. Meanwhile, in medieval Europe, Thomas Aquinas and other scholastic philosophers worked to reconcile the Greek philosophical tradition with Christian theology, developing sophisticated accounts of how God, as a timeless being, could act within and create a temporal universe. These discussions may seem distant from modern physics, but they helped establish certain conceptual distinctions between the eternal and the temporal, between absolute and relational time, between objective and subjective time, that continue to shape how we think about these questions today. By the time of the scientific revolution in the 16th and 17th centuries, a new approach to time was emerging, one that would set aside some of the older philosophical and theological questions and focus instead on what could be measured, calculated, and predicted. The figure who most completely embodied this new approach, and who gave the modern, scientific conception of time its most powerful and influential form, was Isaac Newton. Newton's picture of time was bold, clear, and enormously productive. It allowed him to build a system of mechanics that described the motion of everything from falling apples to orbiting planets with extraordinary precision. And it rested on a conception of time that felt, to most people, completely natural and obvious. Time, for Newton, was absolute. It flowed uniformly and independently. It was the same everywhere in the universe, at the same rate for everyone and everything. No force could speed it up or slow it down. No mass could bend it. No velocity could stretch it. Time was simply there, the universal backdrop against which all events unfolded, ticking away with perfect regularity, whether or not anyone was watching, whether or not anything was moving, whether or not the universe contained anything at all. This is the picture of time that most of us still carry around in our heads. Even today, it feels right. It matches our everyday experience. And for almost every practical purpose in ordinary life, it works perfectly well. But it is wrong. Not wrong in the sense that Newton made a mistake or was careless. Wrong in the sense that the universe turns out to be stranger and more interesting than his picture could accommodate. The challenge to Newton's absolute time came from a young patent clerk in Switzerland who was thinking very carefully about light and whose ideas would change everything. That challenge, and what it revealed about the true nature of time, is where we will go next. Chapter 3. Einstein and the Flexible Clock. In 1905, Albert Einstein was 26 years old and working as a technical examiner at the patent office in Bern, Switzerland. He had no laboratory. He had no university position. He had no team of researchers or access to expensive equipment. What he had was an extraordinary ability to think carefully and deeply about physical problems, and a willingness to follow the logic of his reasoning wherever it led. even when it led somewhere that contradicted everything everyone else believed. In that single year, he published 4 papers that each, individually, would have been enough to establish a major scientific reputation. One of them introduced the special theory of relativity, and the special theory of relativity did something that no one had seriously expected. It showed that time is not absolute. It is not the same for everyone. It does not flow at a fixed universal rate. Time is flexible. It stretches and compresses depending on how fast you are moving. And this is not a trick of perception or a limitation of our measuring instruments. It is a genuine feature of physical reality. To understand how Einstein arrived at this conclusion, we need to start with light. Throughout the 19th century, physicists had been working to understand the nature of light and electromagnetism. James Clerk Maxwell, the Scottish physicist, had developed a set of equations in the 1860s that described how electric and magnetic fields behave and how they produce electromagnetic waves, including light. These equations were extraordinarily successful. They predicted that light travels at a specific speed, approximately 300,000 kilometers per second, and that this speed is a constant. But constant relative to what? In Newtonian physics, speeds are always relative to something. If you are sitting on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing by the tracks would see the ball moving at 150 kilometers per hour. Speeds add together. That is just common sense. So what is the speed of light relative to? Physicists in the 19th century assumed there must be some medium through which light waves traveled, the way sound waves travel through air. They called this medium the luminiferous ether. And if the ether existed, then the speed of light should vary depending on how fast you are moving through it, just as the speed of sound varies depending on how fast you are moving through the air. In 1887, 2 physicists named Albert Michelson and Edward Morley conducted a careful experiment designed to detect the Earth's motion through the ether by measuring whether the speed of light varied in different directions. They found nothing, no variation at all. The speed of light appeared to be the same regardless of how the Earth was moving. This result was deeply puzzling and sat unresolved for nearly 2 decades. Various explanations were proposed, none of them fully satisfying. And then Einstein approached the problem from a completely different direction. Rather than trying to explain why the Michelson-Morley experiment gave the result it did, Einstein simply accepted the result as a fundamental fact about nature and asked what it implied. If the speed of light is the same for all observers, regardless of how they are moving, what must the universe be like? The answer he arrived at was extraordinary. If the speed of light is truly constant for all observers, then the measurements of space and time that different observers make must vary in a compensating way. 2 observers moving relative to each other will measure different lengths for the same object. They will measure different time intervals between the same 2 events. Their clocks, if they start synchronized and then move apart and come back together, will show different elapsed times. And all of these differences are not errors or illusions. They are real physical differences in what each observer actually experiences. This is the phenomenon known as time dilation. A clock that is moving relative to you ticks more slowly than a clock that is stationary relative to you. The faster the relative motion, the greater the slowing. At everyday speeds, the effect is incredibly small, far too small to notice in ordinary life. But at speeds approaching the speed of light, the effect becomes dramatic. Einstein illustrated this with a thought experiment that has become one of the most famous in all of physics. Imagine a pair of twins. One twin stays on Earth. The other boards a spacecraft and travels at a speed close to the speed of light to a distant star and back. When the traveling twin returns, she is aged less than her twin who stayed home, not because of anything biological, not because of any difference in diet or stress or health, but because time itself passed more slowly for her during her journey. She experienced fewer seconds, fewer heartbeats, fewer moments of consciousness. She is genuinely younger than her twin, even though they were born at the same moment. This is not science fiction. It has been verified experimentally. Atomic clocks flown on aircraft around the world and then compared with identical clocks that remained on the ground show exactly the time differences that relativity predicts. Subatomic particles called muons, produced high in the atmosphere by cosmic rays, travel so fast that their internal clocks run slowly enough for them to survive long enough to reach the ground before decaying, something that would be impossible if time ran at the same rate for them as for a stationary observer. Every time a particle accelerator operates, relativistic time dilation is a routine part of the calculations. Time dilation also affects objects that are not moving, but are at different heights in a gravitational field. But that belongs to general relativity, and we will come to it in the next chapter. For now, let us stay with the special theory and what it tells us about the structure of time. One of the deepest implications of special relativity is that there is no universal present. In Newtonian physics, there was a single now that applied everywhere in the universe simultaneously. Every point in space shared the same moment in time. Events that were simultaneous for one observer were simultaneous for all observers. Einstein showed that this is not true. Whether two events are simultaneous depends on the observer's state of motion. Two events that happen at the same time according to one observer may happen at different times according to another observer, moving relative to the first. Neither observer is wrong. There is no preferred frame of reference, no single correct answer to the question of which events are happening now. This has a profound implication that Einstein himself recognized and found deeply significant. If simultaneity is relative, then the division of time into past, present, and future is also relative. What is in your future may already be in someone else's past, depending on how they are moving. The present moment is not a universal fact about the universe. It is a local, observer-dependent concept. Physicists speak of space-time, the unified fabric that combines the three dimensions of space with the single dimension of time into a four-dimensional structure. In space-time, events do not happen at a location in space and a moment in time as two separate things. They happen at a location in space-time, a single point in the four-dimensional continuum. The way different observers slice up space-time into space and time depends on their motion. Just as two people standing at different angles might divide a room differently into left, right, and forward, back, two observers moving at different velocities divide space-time differently into space and time. They agree on the space-time interval between events, the four-dimensional distance between 2 points in space-time, but they disagree on how much of that interval is spatial and how much is temporal. This is a remarkable conclusion. Time is not a universal river flowing at the same rate for everyone. It is one dimension of a four-dimensional structure, and how it is experienced depends on who is experiencing it and how they are moving. Time is real in the sense that it is a genuine dimension of physical reality, but it is flexible, personal, and inseparable from space in a way that Newton never imagined, and that our everyday intuitions do not prepare us for. There is one more implication of special relativity worth noting before we move on. Nothing with mass can travel at the speed of light. As an object accelerates, its effective mass increases, and the energy required to accelerate it further increases as well. Reaching the speed of light would require infinite energy, which is not available. The speed of light is therefore an absolute speed limit built into the structure of space-time. This speed limit is also a time limit, in a sense. It means that information cannot travel faster than light. Cause cannot precede effect. The structure of space-time enforces a causal order on events. Events that could be connected by a signal traveling at or below the speed of light have a definite causal relationship. Events that are too far apart in space for light to connect them within the time interval separating them have no definite causal order. They are what physicists call space-like separated, and their temporal order depends on the observer. All of this emerged from Einstein's willingness to take seriously a single experimental result that everyone else had found puzzling and set aside. By accepting that the speed of light is constant for all observers and following the logic wherever it led, he arrived at a picture of time that is stranger, richer, and more interesting than anything that came before. And he was not finished. Special relativity dealt with observers moving at constant velocities. What about acceleration? What about gravity? Those questions led Einstein to spend the next decade developing the general theory of relativity, which revealed something even more striking about the relationship between time and the physical universe. Chapter 4. Gravity bends time. When Einstein published the special theory of relativity in 1905, he knew immediately that it was incomplete. Special relativity described how time and space behave for observers moving at constant velocities relative to each other. But it said nothing about acceleration, and it said nothing about gravity. Newton had described gravity as a force, a pull between masses that acts instantaneously across any distance. Two objects with mass attract each other, and the strength of that attraction depends on their masses and the distance between them. This description was extraordinarily successful. It explained the orbits of the planets, the behavior of tides, the trajectory of cannonballs. For more than 2 centuries, it stood as one of the greatest achievements of human science. But Newton's gravity sat awkwardly alongside special relativity. Special relativity said that nothing could travel faster than light, that no signal or influence could propagate instantaneously across space. Yet Newtonian gravity appeared to act instantaneously. If the sun were to suddenly disappear, Newton's theory said that the Earth would immediately fly off in a straight line, feeling the absence of the sun's gravity at once, even though the light from the sun's disappearance would not reach us for 8 minutes. That seemed deeply inconsistent with relativity. Einstein spent 10 years, from 1905 to 1915, working to resolve this inconsistency. The result was the general theory of relativity, published in November 1915, and it is one of the most beautiful and profound scientific achievements in human history. The key insight that led Einstein to general relativity began with a simple observation that he later described as the happiest thought of his life. He imagined a person falling freely in free fall, with no floor beneath them. Such a person, Einstein realized, would feel weightless. They would feel no gravitational force at all. Everything around them would fall at the same rate, so there would be no relative motion between them and their surroundings. From the perspective of the falling person, gravity would seem to have disappeared. This equivalence between free fall and the absence of gravity suggested something deeper. What if there is no difference in principle between being in a gravitational field and being accelerated? What if gravity is not a force at all, but something more fundamental, something geometrical? Einstein's answer was that gravity is the curvature of space-time. Mass and energy do not pull on other masses across empty space. Instead, mass and energy curve the fabric of space-time around them, and other objects follow the straightest possible paths through that curved space-time. What we experience as the force of gravity is actually the effect of moving through curved space-time. This is a difficult concept to visualize, but an analogy helps. Imagine a large rubber sheet stretched flat. If you place a heavy ball in the center, the sheet curves downward around it. Now roll a smaller ball across the sheet. Instead of traveling in a straight line, it curves toward the heavy ball, following the contour of the sheet. From above, it looks as if the heavy ball is attracting the smaller one, but there is no force acting between them. The smaller ball is simply following the geometry of the surface. Space-time works similarly, though in 4 dimensions rather than 2, and with a geometry more complex than a rubber sheet. Mass curves space-time. Other objects follow the straightest possible path through that curved space-time, and those paths, when projected into 3-dimensional space, look like orbits or falling trajectories. Now here is the connection to time. If gravity is the curvature of space-time, and time is one of the dimensions of space-time, then gravity curves time as well as space. The closer you are to a massive object, the more space-time is curved around you, and the more slowly time passes for you relative to someone farther away. This effect is called gravitational time dilation, and it is distinct from the velocity-based time dilation of special relativity. Both are real, both have been measured, and they operate simultaneously, each contributing to the total difference in clock rates between observers in different situations. The closer you are to a massive object, the more slowly your clock ticks relative to a clock farther away. At the surface of the Earth, time runs very slightly more slowly than it does at higher altitudes. The difference is tiny, far too small to notice in everyday life. But it is measurable. In fact, it must be accounted for in the global positioning system, the network of satellites that provides the navigation data used by phones, aircraft, ships, and countless other devices. GPS satellites orbit at an altitude of about 20,000 kilometers. At that altitude, they are farther from Earth's center of gravity than we are at the surface, so their clocks run slightly faster due to reduced gravitational time dilation. At the same time, they are moving at high orbital velocities, so their clocks run slightly slower due to velocity-based time dilation from special relativity. The two effects do not cancel each other out. The net result is that GPS satellite clocks gain about 38 microseconds per day relative to clocks on the ground. 38 microseconds sounds trivial, but GPS navigation works by timing signals with extraordinary precision. An error of 38 microseconds accumulated each day without correction would cause GPS positioning errors that would grow at a rate of about 10 kilometers per day. Within weeks, the system would be useless. The GPS system corrects for relativistic time dilation as a matter of routine. Every time you use navigation on your phone, you are relying on Einstein's general theory of relativity. Time dilation is not just a theoretical curiosity, it is an engineered reality. The gravitational time dilation effect becomes more pronounced as you approach more massive objects. Near the surface of a neutron star, whose gravity is billions of times stronger than Earth's, clocks would run dramatically more slowly than clocks far away. And near a black hole, as we approach the event horizon, the effect becomes extreme. For an observer watching from a safe distance, A clock falling toward a black hole would appear to slow down progressively as it approached the event horizon, the boundary beyond which nothing can escape. The clock would seem to tick more and more slowly, its rate approaching zero, freezing asymptotically at the horizon. From the distant observer's perspective, the falling clock never quite reaches the event horizon. It simply slows down and fades. From the perspective of the clock itself, however, nothing unusual happens at the event horizon. It crosses the boundary in finite time and continues falling. The extreme time, dilation, is a feature of the view from outside, not the experience from inside. This asymmetry between what different observers experience as the same sequence of events is one of the most striking features of general relativity, and one of the clearest demonstrations that time is not a single universal thing. Different observers, in different positions in a gravitational field, genuinely experience different amounts of time. Their clocks measure different intervals. Their lives unfold at different rates relative to each other. Time is local, not global. It belongs to each observer's own path through space-time. General relativity also makes a broader and even more striking claim. The universe itself, as a whole, has a geometry. That geometry evolves over time, and the history of that evolution, traced backward, leads to a singularity, a point of infinite density and curvature, at which the equations of general relativity break down. That singularity is what we call the Big Bang. And one of the most profound questions that general relativity raises is whether time itself began at the Big Bang, or whether time existed before it in some form that our current equations cannot describe. We will return to that question in a later chapter. For now, the picture that has emerged from both special and general relativity is clear. Time is not what Newton thought it was. It is not an absolute universal backdrop flowing at the same rate everywhere. It is a dimension of space-time, curved by mass and energy, stretched by velocity, local to each observer's path through the universe. Two clocks that start together and follow different paths through space-time will show different elapsed times when they meet again. That difference is not an error. It is a precise, predictable, measurable feature of physical reality. And yet, for all that we have learned about how time behaves, there is one feature of time that neither special nor general relativity fully explains. That is the fact that time seems to have a direction. The past is different from the future. Things happen in sequence. Causes precede effects. You can remember yesterday, but not tomorrow. You can stir cream into coffee, but not unstir it. The universe seems to have a strong preference for one direction of time over the other. Why that should be, given that the fundamental laws of physics are largely symmetric in time, is one of the deepest puzzles in all of science. And it is the question we turn to next. Chapter 5. The Arrow of Time. There is a simple experiment you can do in your mind. Imagine watching a video of a glass falling off a table and shattering into pieces on the floor. You would have no difficulty recognizing which direction the video was playing. The glass falls, hits the floor, breaks apart, and the pieces scatter. That sequence is immediately recognizable as forward in time. Now imagine watching the video played in reverse. The pieces gather themselves up from the floor, assemble into a whole glass, and leap back up onto the table. You would recognize instantly that something was wrong. That sequence does not happen in nature. It is obviously backward. This seems trivially obvious. Of course, time moves forward. Of course, broken glasses do not reassemble themselves. Of course, spilled milk does not flow back into the glass. These things are so basic to our experience that they barely seem worth saying. But here is what makes this deeply puzzling. If you look at the fundamental laws of physics, the equations that govern the behavior of particles at the microscopic level, almost all of them work equally well in both directions of time. The laws of motion, the laws of electromagnetism, the laws of quantum mechanics, all of them are time symmetric. If you took a movie of a collision between two particles and ran it backward, the reversed movie would also show a perfectly valid physical process, one that obeys all the known laws of physics. So why does the large-scale world have such a strong preference for one direction of time? Why does the universe behave so differently in the forward direction than in the reverse direction, if the underlying laws do not distinguish between them? This puzzle is what physicists call the problem of the arrow of time. The most widely accepted answer to this question involves a concept from thermodynamics called entropy. Entropy is, roughly speaking, a measure of disorder or randomness in a system. A glass sitting intact on a table is in a highly ordered state. The atoms that make it up are arranged in a very specific, structured way. There are relatively few arrangements that would look like an intact glass, but there are an enormous number of arrangements that would look like scattered shards of glass on a floor. When the glass breaks, it moves from one of the rare ordered arrangements to one of the vastly more common disordered ones. The second law of thermodynamics states that the entropy of a closed system tends to increase over time. Disorder tends to increase. Ordered arrangements tend to give way to disordered ones, simply because there are so many more disordered states available. The glass does not reassemble itself because the probability of all those scattered pieces spontaneously moving in exactly the right ways to form an intact glass is so vanishingly small as to be, for all practical purposes, impossible. This is the thermodynamic arrow of time. The direction from past to future is the direction in which entropy increases. The past is the direction of lower entropy. The future is the direction of higher entropy. And this asymmetry, rooted in statistics and probability, gives time its apparent direction at the macroscopic level, even though the microscopic laws are symmetric. But this answer, satisfying as it is in many ways, immediately raises a deeper question. Why was entropy low to begin with? If disorder tends to increase, and the universe has been running for almost 14 billion years, why has entropy not already reached its maximum value? Why is there still structure, still stars and galaxies and planets and life, rather than a uniform soup of particles at maximum entropy? The answer has to be that the universe started in an extraordinarily low entropy state. The Big Bang, whatever it was, produced a universe of remarkable order and structure. The expansion of the universe since then has been, in a deep sense, the story of that initial order, gradually spreading out and dissipating, entropy increasing step by step as stars burn their fuel and radiate heat into space. But this just pushes the question back further. Why did the universe begin in such a low entropy state? That is one of the deepest unanswered questions in cosmology, and we will return to it when we discuss the beginning of time in a later chapter. There are other arrows of time besides the thermodynamic one, and they are worth considering because they show how pervasive the directionality of time is throughout physics and experience. There is the causal arrow of time. Causes precede their effects. A stone thrown into a pond creates ripples that spread outward. Ripples do not spontaneously gather from the edges of a pond and converge on a single point, lifting a stone out of the water. Information flows from past to future, not from future to past. The causal structure of the universe is deeply asymmetric in time. there is the radiative arrow of time. When a light bulb turns on, it emits light that spreads outward in all directions. We never see light spontaneously converging from all directions onto a light bulb, flowing into it and turning it on. Radiation spreads outward from sources, not inward toward them. This asymmetry is connected to the thermodynamic arrow, but it manifests in a particularly clear and striking way. There is the cosmological arrow of time. The universe is expanding. Galaxies are moving apart. The universe in the past was smaller, denser, and hotter than it is today. This gives a clear direction to cosmic time, from the dense, hot past toward the increasingly sparse and cool future. And there is the psychological arrow of time, perhaps the most immediately familiar of all. We remember the past and not the future. We feel time moving from yesterday toward tomorrow. Our sense of the present moment moving forward, of time flowing, is one of the most basic features of conscious experience. And this psychological arrow appears to be aligned with the thermodynamic arrow. We remember the past because the past has left traces, records, memories, low entropy structures that encode information about what happened. The future has not yet left any such traces. The philosopher of physics Hugh Price has argued that all of these arrows of time are ultimately connected, that they all trace back to the single deep fact that the universe began in an extraordinarily low entropy state. If the universe had begun in a high entropy state, or if it were in thermal equilibrium throughout, there would be no arrow of time. Events would be as likely to run in one direction as the other. There would be no difference between past and future. There would be no thermodynamic processes, no causal chains, no memories, no life. It is worth pausing here to appreciate how strange this situation is. The directionality of time, that quality which seems so fundamental and undeniable from the inside, the fact that you remember your childhood and not your old age, that eggs break but do not unbreak, that the future is open and the past is closed. All of this appears to be a consequence not of the fundamental laws of physics, which do not require it, but of the particular initial conditions of our universe. Time's arrow is, in a sense, an accident of history, a consequence of the remarkably ordered beginning from which our universe emerged. Some physicists and philosophers find this unsatisfying. Surely, they argue, there should be a deeper explanation for why time has a direction, one that does not merely push the mystery back to the initial conditions of the Big Bang. Various proposals have been made, involving quantum cosmology, the multiverse, and other frameworks, but none has achieved broad acceptance. Others find the thermodynamic explanation genuinely illuminating, even if it does not provide the kind of deep necessity one might hope for. The universe had a low entropy beginning. Entropy has been increasing ever since, and that is why time has a direction. It may not feel like a complete explanation, but it is a real one, grounded in physics and supported by evidence. What both sides agree on is this: the arrow of time is real. It shapes every aspect of our experience. It is built into the structure of causation, memory, and physical processes at every scale. And yet, it is not built into the fundamental equations of physics in the way we might expect. The laws of physics are largely indifferent to the direction of time. The arrow emerges from something else, from the structure of the universe we happen to inhabit, from the particular history of a cosmos that started from an extraordinarily improbable beginning. That beginning, and what it tells us about the nature of time, is a question we will return to. But first, there is another aspect of time that deserves careful attention. Not the direction of time, but its very existence as something that flows or moves. We say that time passes, that moments come and go, that the present is always moving forward into the future. But is that picture of flowing time physically real, or is it something else entirely? Chapter 6. Does time actually flow? Of all the things we say about time, the most common and the most natural is that it flows. Time passes. Moments come and go. The present moves steadily forward, leaving the past behind and approaching the future. This sense of flow, of movement, of the now progressing through time like a spotlight moving along a stage, is perhaps the most immediate and undeniable feature of our experience of time. And yet, when physicists and philosophers examine this idea carefully, they find it deeply problematic. The notion of flowing time, taken seriously, turns out to be either empty or incoherent, and the alternative picture that physics suggests is one that many people find profoundly strange and difficult to accept. Let us start with the problem. When we say that time flows, we mean that it moves. But movement is something that happens in time. A river flows because its water occupies different positions at different moments. Movement requires time to measure it. So if time itself flows, what does it flow through? What is the medium through which time moves, and at what rate does it flow? That last question is particularly revealing. We might say that time flows at 1 second per second, but that is not a rate in any meaningful sense. A rate is a ratio of two different quantities, like meters per second or kilometers per hour. 1 second per second is just the number 1, with no units attached. It says nothing at all about how fast time is moving, because there is nothing to compare the passage of time to except itself. The philosopher D.C. Williams pointed out this problem clearly in the mid-20th century. The flowing time picture, he argued, requires us to imagine a second dimension of time, a meta-time through which ordinary time flows. But then we would need a third dimension of time for the meta-time to flow through, and so on forever. The idea of flowing time leads to an infinite regress that solves nothing. So what is the alternative? The alternative, which emerges naturally from the physics of relativity, is what philosophers call the block universe, or eternalism. In this picture, time does not flow. The past, present, and future all exist equally and simultaneously, laid out in a four-dimensional space-time block. Events do not come into existence and then pass away. They simply exist at their location in space-time, the way cities exist at their locations on a map. In the block universe, the Big Bang exists. Your birth exists. This present moment exists. Your death exists. All of these events are equally real, equally present in the space-time block. The difference between past, present, and future is not a difference in reality or existence. It is a difference in location within the four-dimensional structure. You experience time as flowing because you are a physical process moving along a world line through space-time. Your world line is the path your body traces through the four dimensions of space-time from birth to death. At each point along that world line, you have access to memories of earlier points, but not later ones, because of the thermodynamic arrow of time we discussed in the previous chapter. This asymmetry in your access to information along your world line is what creates the experience of moving through time, of the past being gone and the future being ahead. But in the block universe, nothing is actually moving. The universe is not a film being played through a projector, with one frame lit up as the present, while the others wait in darkness. All the frames exist simultaneously. What we call the present moment is simply the location in space-time, where a particular observer's world line happens to be at a particular point. This picture is deeply counterintuitive. It means that your future already exists. The things that have not happened yet from your perspective are not waiting to come into being. They already exist in space-time, at locations you have not yet reached along your world line. It means that the people and things you have lost to the past are not truly gone. They exist in their locations in space-time, as real as ever, simply at coordinates you can no longer access. Some people find this idea strangely comforting. Others find it deeply troubling, because it seems to eliminate any meaningful sense of becoming, of the universe unfolding and changing, of the future being genuinely open. If everything already exists in the block, in what sense is anything new ever happening? This brings us to one of the central debates in the philosophy of time, between eternalism and what philosophers call presentism. Presentism holds that only the present moment is real. The past no longer exists. The future does not yet exist. Reality is constituted entirely by what is happening now. Time flows because the present moment is constantly being replaced by a new present moment, the future becoming present and the present receding into the past. On this view, the block universe is simply wrong. Past and future are not equally real. Only now is real. Presentism matches our intuitions very well. It captures what time feels like from the inside, but it faces serious difficulties when confronted with the physics of relativity. As we saw in the chapter on Einstein, simultaneity is relative. Different observers moving at different velocities have different present moments. There is no single global now that all observers share. If only the present is real, and different observers have different presents, then what counts as real becomes observer-dependent in a way that is very hard to make coherent. A third position, between pure eternalism and presentism, is called the growing block universe. In this picture, the past and present are both real, existing in a space-time block that is constantly growing as new events occur. The future, however, does not yet exist. The block has a leading edge, the present moment, beyond which there is nothing yet. Time moves forward in the sense that the block grows, new events coming into existence and joining the permanent record of the past. The growing block universe preserves the intuition that the future is genuinely open, that things have not yet been determined, while also preserving the reality of the past as something fixed and permanent. But it too faces challenges from relativity, since the notion of a universal leading edge, a global present moment at which the block is currently growing, conflicts with the relativity of simultaneity. None of these positions is without difficulties. Eternalism handles relativity well, but seems to eliminate genuine becoming and the openness of the future. Presentism preserves our intuitions about time, but struggles to accommodate relativity. The growing block tries to find a middle path, but runs into its own problems with relativistic simultaneity. What this debate reveals is something important. The flow of time, that feature of our experience that seems so undeniable and immediate, may not correspond to anything in the physical world. Physics describes a space-time structure. It does not describe a moving spotlight of nowness traveling through that structure. The sense that time is flowing, that the present is special, that the past is gone and the future is coming, may be a feature of consciousness rather than a feature of physics. This does not mean the experience is unreal or unimportant. Conscious experience is the most immediate reality we have access to, but it may mean that our experience of time as flowing is something our minds construct, a way of navigating a static four-dimensional structure from the inside, rather than a direct perception of how things truly are. The physicist Carlo Rovelli has written beautifully about this. He argues that what we call the flow of time is the result of our particular perspective as thermal beings embedded in a universe with a thermodynamic arrow. We are not outside time looking at it flow. We are processes within time, and our sense of time flowing is the subjective feel of those processes unfolding along the thermodynamic gradient from low entropy past to high entropy future. The philosopher of physics Tim Maudlin takes a different view. He argues that the passage of time is a genuine and fundamental feature of reality, not something to be explained away or reduced to something else. Time really does pass, he argues, and any physics that fails to capture that is incomplete. The block universe, for Maudlin, leaves something important out. This debate is ongoing. There is no consensus among physicists or philosophers about whether time genuinely flows, whether the present moment is physically special, or whether the block universe is the correct picture of reality. What there is, instead, is a genuine and deep puzzle about the relationship between the physical description of time and the experienced reality of time. And that gap between what physics says and what experience feels like is not a small or trivial thing. It sits at the heart of some of the deepest questions about the nature of consciousness, the nature of reality, and ultimately the nature of time itself. We have been exploring time from the outside, in a sense, looking at what physics and philosophy have to say about its structure and direction and flow. In the chapters ahead, we will go smaller, into the quantum world, where time behaves in ways that are stranger still, and we will go further back, to the beginning of the universe, to ask whether time itself had an origin. But first, let us acknowledge where we are. We are creatures who live inside time, who feel it passing, who are shaped by it in every moment of our existence. And we are asking, with genuine seriousness, whether that feeling corresponds to anything real in the fabric of the universe. That is one of the most remarkable questions a conscious being can ask. And the fact that we cannot yet answer it definitively is not a failure. It is an invitation to keep looking. Chapter 7. Time and Quantum Mechanics. If the theory of relativity made time strange, quantum mechanics makes it stranger still. Relativity showed us that time is flexible, local, and inseparable from space. Quantum mechanics raises questions about whether time is fundamental at all, whether it might be something that emerges from deeper processes that are themselves timeless, and whether the familiar picture of events unfolding in sequence might break down entirely at the smaller scales of reality. To appreciate what quantum mechanics says about time, it helps to first understand something about what quantum mechanics says about reality in general. Classical physics, the physics of Newton and Maxwell, describes a world of definite properties. A particle has a definite position. It moves along a definite path. It has a definite velocity at every moment. Before we measure it, it was somewhere specific, doing something specific. Measurement simply reveals what was already there. Quantum mechanics overturns this picture in a fundamental way. In the quantum world, particles do not have definite properties until those properties are measured. Before measurement, a particle exists in what is called a superposition, a combination of multiple possible states simultaneously. It does not have a definite position. It has a range of possible positions, each with a certain probability. When a measurement is made, the superposition resolves into a single definite outcome. But before the measurement, the definite outcome simply did not exist. This is not a statement about our ignorance. It is not that the particle had a definite position all along, and we just did not know what it was. The mathematics of quantum mechanics and a great deal of experimental evidence suggests that the indefiniteness is real. The particle genuinely did not have a definite position before it was measured. Now, what does all of this have to do with time? The first and most immediate connection is that quantum mechanics treats time differently from the other dimensions of spacetime. In quantum mechanics, position, momentum, energy, and spin are all quantum observables. They are represented by mathematical operators, and they can be indefinite, existing in superpositions. But time, in standard quantum mechanics, is not an observable in this sense. It is a parameter, a classical background variable against which quantum events unfold. Time is the stage, not an actor. This asymmetry is deeply uncomfortable. Relativity tells us that time and space are aspects of a single unified structure, equally fundamental, equally physical. But quantum mechanics treats space and time very differently. Position is a quantum observable. Time is not. This inconsistency between quantum mechanics and relativity is one of the central tensions in modern physics, and resolving it is one of the great challenges facing theoretical physicists today. When physicists attempt to combine quantum mechanics with general relativity to build a theory of quantum gravity, they run into a problem so severe that it has a name. It is called the problem of time. In general relativity, there is no fixed background time. Time is dynamic, shaped by matter and energy, different for different observers. But quantum mechanics requires a fixed background time against which the quantum state evolves. When you try to write down the equations of quantum gravity, time seems to disappear entirely. The equation at the heart of quantum cosmology, the Wheeler-DeWitt equation, describes the quantum state of the entire universe. And in that equation, there is no time variable. The equation is static. It describes a quantum state that does not evolve. The universe, at the most fundamental level of quantum gravity, appears to be timeless. This is one of the most striking and puzzling results in all of theoretical physics. The universe, described at the deepest level we currently have access to, does not appear to contain time as a fundamental ingredient. Time, it seems, must somehow emerge from this timeless quantum state rather than being built in from the start. How might that emergence work? Several proposals have been made. One influential idea, developed by the physicists Don Page and William Wouters in the 1980s, suggests that time emerges from quantum entanglement. In their framework, the universe is in a static quantum state, with no overall time evolution. But parts of the universe can become entangled with each other, and an observer within one part of the universe, using another part as a clock, will experience a genuine sense of time passing. Time, in this picture, is relational. It is not a property of the universe as a whole, but something that arises from the correlations between different parts of it. This idea has been explored experimentally in recent years, and some physicists find it genuinely promising. Others remain skeptical, but it represents a serious and interesting possibility that time is not a fundamental feature of reality, but an emergent one, arising from the quantum structure of the universe the way temperature arises from the motion of atoms. Temperature is not a fundamental property of individual atoms. It emerges from the collective behavior of large numbers of them. Perhaps time is similar. There is another aspect of quantum mechanics and time worth exploring, which is the question of time symmetry at the quantum level. As we discussed in the chapter on the arrow of time, most fundamental physical laws are symmetric under time reversal. If you run the equations backward, you get equally valid physics. Quantum mechanics is largely the same way. The Schrödinger equation, which describes how quantum states evolve, is time symmetric. If you reverse the direction of time in the equation, it still produces valid solutions. There is, however, one important exception. The process of measurement in quantum mechanics, sometimes called the collapse of the wave function, is not time-symmetric. Before measurement, a quantum system exists in a superposition of states. After measurement, it is in a definite state. This transition from superposition to definite outcome appears to be irreversible. You cannot uncollapse a wave function the way you cannot unbreak a glass. Some physicists argue that wave function collapse is a real physical process, and that it introduces a genuine arrow of time at the quantum level. Others argue that wave function collapse is not a real physical process at all, that it is an artifact of how we describe measurement rather than something that actually happens in the world. In the many worlds interpretation of quantum mechanics, for example, there is no collapse. When a measurement is made, the universe branches into multiple versions, one for each possible outcome. All outcomes occur. The wave function never collapses, and the equations remain time-symmetric throughout. The many worlds interpretation has striking implications for time. In this picture, every quantum event that has multiple possible outcomes causes the universe to branch. The universe is constantly splitting into a vast, perhaps infinite, proliferation of parallel branches, each representing a different sequence of quantum outcomes. Time, in this picture, is not a single linear thread from past to future. It is a constantly ramifying tree, branching at every quantum junction. Whether the many worlds interpretation is correct is a matter of ongoing debate. It is mathematically elegant and avoids some of the conceptual difficulties of wave function collapse. But it comes with its own challenges, including the difficulty of explaining why we observe definite outcomes at all, rather than experiencing the branching directly, and the challenge of making sense of probability in a framework where all outcomes occur. There is one more aspect of quantum mechanics and time that deserves attention, which is the phenomenon of quantum tunneling. In classical physics, a particle cannot pass through a barrier if it does not have enough energy to go over it. In quantum mechanics, a particle can tunnel through a barrier even without the necessary energy, appearing on the other side as if it had passed through the barrier rather than over it. This tunneling process can appear to be instantaneous, or even to involve the particle traveling backward in time in some interpretations. Quantum tunneling is not just a theoretical curiosity. It is responsible for nuclear fusion in stars, for the radioactive decay of atomic nuclei, and for the operation of many electronic devices. It is a real and important phenomenon. And while the time aspects of tunneling are still debated, with different interpretations giving different answers about how long the tunneling process takes, the phenomenon raises genuine questions about the smoothness and linearity of time at the quantum scale. What emerges from all of this is a picture of time in quantum mechanics that is fragmentary, puzzling, and in many ways unresolved. Time appears to be treated differently from space, in tension with the lessons of relativity. At the deepest level of quantum gravity, time may not be fundamental at all, emerging instead from the quantum correlations between parts of a timeless universe. The process of measurement introduces an apparent irreversibility that sits awkwardly with the time symmetry of the underlying equations. And different interpretations of quantum mechanics give very different pictures of what time is and how it behaves. Quantum mechanics does not give us a clean answer to the question of what time is. What it gives us instead is a deeper appreciation of how strange and unresolved the question remains, even after a century of extraordinary progress in our understanding of the physical world. The universe, at its smallest and most fundamental scales, does not appear to have a simple, clear relationship with time, and that strangeness at the bottom propagates upward, casting its shadow over every other aspect of the question we are exploring tonight. With that strangeness in mind, let us turn to the largest scale question of all, not how time behaves within the universe, but whether time itself had a beginning. Chapter 8. The Beginning of Time. There is a question that has haunted human thought for as long as people have been capable of asking it. Did the universe have a beginning? And if it did, what came before? These questions feel natural and almost unavoidable. We live in a world where everything we encounter has a beginning. People are born. Rivers begin at their sources. Storms form and dissipate. Every story has a first page. The idea that the universe itself might have had a first moment, a point before which there was nothing, feels both compelling and deeply strange. For most of human history, this question was primarily a theological and philosophical one. Various religious traditions offered creation narratives, accounts of how the universe came into being from nothing, or from a primordial chaos, or through the action of a divine will. Philosophers debated whether the universe was eternal or created, whether time had always existed, or whether it too had a beginning. The ancient Greek philosopher Aristotle argued that the universe was eternal. It had always existed and would always exist. The idea of a beginning seemed to him to require a cause, and that cause would itself require a cause, leading to an infinite regress. An eternal universe avoided this problem. Time, for Aristotle, was infinite in both directions, extending without limit into the past and into the future. Augustine, as we saw in an earlier chapter, took a different view. He argued that time itself was created along with the universe, and that the question of what existed before the creation was therefore malformed. There was no before, because time itself began at the moment of creation. For many centuries, the debate between these positions was conducted largely on philosophical and theological grounds, with little input from empirical science. That changed dramatically in the 20th century, when observational astronomy and theoretical physics together produced a picture of cosmic history that pointed unmistakably toward a beginning. The key observation came in the 1920s, when the American astronomer Edwin Hubble made a discovery that transformed our understanding of the universe. By carefully studying the light from distant galaxies, Hubble found that almost all of them were moving away from us, and that the farther away a galaxy was, the faster it was receding. The universe was expanding. This discovery had an immediate and profound implication. If the universe is expanding now, then in the past it was smaller. Run the expansion backward in time, like a film played in reverse, and the galaxies converge, the universe contracts, everything comes together into an increasingly dense and hot state. Continue backward far enough, and you reach a point of extraordinary density and temperature, a state so extreme that our current physical theories break down trying to describe it. That point, approximately 13.8 billion years ago, is what we call the Big Bang. It is not an explosion in space, as the name might suggest. It is the expansion of space itself, beginning from an extremely hot and dense state, and continuing ever since. Every galaxy, every star, every atom in your body traces its history back to that initial state. The Big Bang is now supported by an enormous weight of observational evidence. The expansion of the universe, the cosmic microwave background radiation, the faint glow of heat left over from the early universe that permeates all of space, the abundances of light elements like hydrogen and helium, which match precisely the predictions of Big Bang nucleosynthesis. The large-scale structure of the universe, the distribution of galaxies and galaxy clusters, which reflects the initial conditions of the early cosmos. All of these lines of evidence converge on the same picture. But the Big Bang raises the question of time in a particularly sharp and urgent way. If the universe began in the Big Bang, did time begin then too? Or did time exist before the Big Bang, perhaps in some form we cannot currently describe or access? Within the framework of general relativity, the answer appears to be that time did begin at the Big Bang. General relativity describes the universe as a four-dimensional space-time, and when you trace that space-time backward in time, following the equations of general relativity, you reach a singularity, a point at which the curvature of space-time becomes infinite and the equations break down. At that singularity, time itself comes to an end, or rather, to a beginning. There is no before, because the singularity marks the boundary of space-time. Time, along with space, began at the Big Bang. This conclusion is supported by the singularity theorems developed by Roger Penrose and Stephen Hawking in the 1960s and 1970s. These theorems showed that, under very general conditions, a universe like ours must have begun in a singularity. The theorems are mathematically rigorous and were a major achievement, and they strongly suggest that time had a beginning. But there is an important caveat. The singularity theorems are theorems of general relativity, and general relativity, as we have seen, breaks down at the extreme conditions near the singularity. At those scales, quantum effects become important, and a complete theory of quantum gravity is needed to describe what was happening. We do not yet have such a theory, so while general relativity points toward a beginning of time, it cannot tell us with confidence what happened at or before the moment of the Big Bang. Stephen Hawking, working with the physicist James Hartley, proposed one of the most imaginative responses to this problem. Their no-boundary proposal, developed in the early 1980s, suggested that the universe has no boundary in time, no initial singularity, no moment of creation in the conventional sense. Instead, near the beginning of the universe, time behaves more like a spatial dimension. The distinction between time and space becomes blurred. The universe does not begin at a point. It rounds off smoothly, the way the surface of the Earth rounds off at the South Pole. At the South Pole, there is no edge to the Earth. There is no point south of the South Pole. The surface simply curves around, and the southward direction ceases to have meaning. In the Hartle-Hawking picture, something similar happens at the beginning of the universe. There is no initial boundary, no moment before which there was nothing. Time gradually emerges from a state that is more spatial in character, without there being a specific first moment. If the Hartle-Hawking proposal is correct, then the question of what came before the Big Bang is as malformed as the question of what is south of the South Pole. Not because the question is unanswerable, but because the concepts it relies on simply do not apply in that region. Before loses its meaning when time itself is still emerging. This idea has a remarkable resonance with Augustine's ancient philosophical argument. 1400 years before Hawking and Hartley, Augustine suggested that the question of what God was doing before the creation was malformed, because time itself was part of creation. The Hartle-Hawking proposal reaches a similar conclusion through entirely different means, through the mathematics of quantum cosmology, rather than theological reasoning. Other proposals for the origin of time include the idea of a bouncing universe, in which the Big Bang was not a true beginning, but a transition from a previous contracting phase. In this picture, the the universe contracts to a very small but not infinitely dense state, bounces, and then expands again. The Big Bang is the bounce, not the beginning. Time extends through the bounce into a previous era, a contracting universe that preceded our expanding one. Various versions of this idea have been developed, including loop quantum cosmology and the ekpyrotic model, which invokes the collision of higher dimensional structures called branes. These models are speculative and not yet confirmed by observation, but they represent serious scientific proposals for how time might extend beyond the Big Bang. There is also the possibility that our universe emerged from a larger structure, perhaps a multiverse, in which our Big Bang was a local event within a broader space-time. In eternal inflation models, the universe as a whole inflates forever, with individual regions like our observable universe forming as bubbles within the eternally inflating background. In this picture, our Big Bang had a before, even if we cannot observe it, because our observable universe is just one bubble in an infinite sea of inflating space-time. What all of these proposals share is a recognition that the question of the beginning of time is not settled, that our current best theories push us to the edge of what we can describe and then break down, and that the answer, when it comes, will likely require a fundamental revision of our understanding of time, space, and the quantum nature of the universe. We are, in a genuine sense, at the frontier here. The question of whether time had a beginning is one of the deepest questions in all of science, and we do not yet have a definitive answer. What we have is a remarkable convergence of evidence pointing toward a beginning, approximately 14 billion years ago, combined with serious theoretical reasons to suspect that our current understanding of time breaks down near that beginning, and a collection of imaginative and mathematically serious proposals for what might lie beyond it. The honest answer to the question of what came before the Big Bang is this: we do not know. We are not certain that the question has a meaningful answer, and we are not even certain that our concept of time, as something that flows from past to future, as something that can be extended indefinitely in both directions, applies in the extreme conditions near the origin of the universe. That uncertainty is not a failure. It is a marker of where the frontier lies, and it points toward the need for a deeper understanding of time, one that goes beyond both general relativity and quantum mechanics as we currently know them, toward whatever theory of quantum gravity eventually emerges to replace them. Chapter 9. The Perception of Time. We have spent much of this journey looking at time from the outside, examining what physics and philosophy have to say about its structure, its direction, its possible beginning, and its fundamental nature. Now we turn inward, because whatever time is in the physical world, there is another dimension to the question that is equally real and equally puzzling. The dimension of experience. You do not just exist in time. You feel it. You have a rich, textured, moment-by-moment sense of time passing. Hours can feel like minutes. Minutes can feel like hours. A single vivid memory can seem to compress years into a single image. A long afternoon of waiting can stretch out until it feels almost unbearable. The experience of time is not a passive registration of clock ticks. It is an active construction, something your brain produces, shapes, and sometimes distorts in remarkable ways. Understanding how the brain constructs the experience of time is one of the most fascinating areas of modern neuroscience, and what that research reveals has interesting implications for the broader question of what time is, because it suggests that at least some of what we take to be features of time itself may actually be features of the minds that perceive it. Let us begin with the most basic level. How does the brain track time at all? The brain does not have a single centralized clock the way a computer does. There is no dedicated timekeeping organ that runs continuously and stamps every experience with a precise timestamp. Instead, the brain uses multiple overlapping systems to track time at different scales, from the millisecond timing needed for speech and music to the circadian rhythms that regulate sleep and wakefulness over the course of a day. At the scale of seconds and minutes, the brain relies on a network of regions, including the basal ganglia, the cerebellum, and the prefrontal cortex. These regions work together to estimate durations, to sequence events, and to develop a sense of how much time has passed. The neurotransmitter dopamine plays an important role in this system. When dopamine levels are high, time tends to feel like it is passing more quickly. When dopamine levels are low, time tends to feel slower. This is one reason why activities that are engaging and rewarding, which trigger dopamine release, tend to make time feel like it is flying by. At the scale of hours and days, the brain is governed by the circadian clock, a roughly 24-hour biological rhythm, driven by a small cluster of neurons in the hypothalamus, called the suprachiasmatic nucleus. This internal clock is synchronized to the external world primarily through light, which is detected by specialized cells in the retina and used to adjust the timing of the circadian rhythm. When you travel across time zones and experience jet lag, you are feeling the misalignment between your internal circadian clock and the external time of the new location. But beyond these physiological mechanisms, there is a deeper and more interesting question. How does the brain construct the sense of a continuous flow of time? The feeling that moments are connected, that now is always arriving out of the past and heading toward the future. The psychologist William James, writing in the late 19th century, introduced the concept he called the specious present. James observed that we do not experience time as a series of isolated instants, each completely separate from the next. Instead, we experience a kind of window of time, a brief interval that feels like the present moment, but actually encompasses a short span of the recent past and the near future. The specious present is the felt duration of now, the temporal window within which experience feels unified and immediate. Modern research suggests that this window is roughly 2 to 3 seconds long for most people, though it varies with context. Within this window, events are perceived as simultaneous or closely connected. Outside it, they begin to feel like past or future. The brain actively integrates information from this window into a coherent experience of the present moment, stitching together sounds, sights, touches, and thoughts into a unified now. This stitching process has some remarkable properties. One of the most striking is that the brain does not always process information in the order in which it arrives. Visual information, for example, takes longer to process than some other kinds of sensory information. The brain has to compensate for these processing delays to produce a coherent experience of simultaneous events. It does this by slightly backdating some experiences, adjusting the perceived timing of events to make them feel simultaneous, even when the raw neural signals arrived at slightly different times. This means that what you experience as happening now is actually a reconstruction, an edited version of events that the brain has adjusted and smoothed to produce a coherent narrative. The present moment, as you experience it, is already slightly in the past by the time it reaches your awareness. This is a genuinely strange conclusion. The vivid sense of being in the present moment, of experiencing things as they happen, turns out to be a kind of controlled illusion, a neural reconstruction of recent events that is presented to consciousness as if it were happening right now. The felt immediacy of the present is real, but its precision is limited and its timing is adjusted by the brain for coherence. The experience of duration, how long things feel like they last, is equally constructed and equally variable. A fundamental factor in perceived duration is the amount of information the brain processes during an interval. When you are in an unfamiliar environment, paying close attention, having new experiences, your brain is processing a great deal of information. That richness of processing makes the interval feel longer in retrospect. When you are in a familiar routine, doing things automatically without much conscious attention, less information is being processed, and the interval feels shorter in retrospect. This is why childhood summers feel endless in memory, while years in adulthood can seem to compress into almost nothing. A child encountering the world for the first time is processing enormous amounts of novel information. An adult following familiar routines is processing much less. The density of memory, the richness of encoded experience, shapes how long an interval feels when you look back on it. The same principle explains why frightening or emotionally intense experiences can seem to slow down time. In a moment of sudden danger, the brain shifts into a heightened state of alertness, processing information with exceptional speed and detail. The amygdala, a region involved in emotional processing and threat detection, becomes highly active. More information is encoded per unit of having fun, and it reflects the same having fun, and it reflects the same underlying principle, but in reverse. When you are deeply engaged in an enjoyable activity, attention is directed outward, toward the activity itself. Less attention is available for tracking the passage of time. The brain processes fewer temporal cues. The interval feels shorter in the moment, though in retrospect it may feel richly full. Sleep presents a particularly interesting case for the experience of time. During deep, dreamless sleep, the experience of time seems to vanish entirely. You close your eyes, and then, with no sense of duration, no felt passage of moments, you open them again, and hours have passed. There is no subjective experience of those hours. They are simply absent from consciousness. This is one of the clearest examples of something we tend to gloss over in everyday life. The experience of time is not continuous. It is not a steady stream that runs from moment to moment without interruption. It is punctuated by gaps, by periods of unconsciousness in which time passes without being experienced at all. Sleep is the most familiar of these gaps, but anesthesia, certain kinds of seizures, and other states of altered consciousness produce similar effects. What does it mean for time to pass without being experienced? From the outside, the clocks kept ticking, the earth kept rotating, events kept occurring. Time passed in the physical sense, but from the inside there was nothing. No duration, no flow, no sense of movement from moment to moment. The subjective experience of time, the felt passage of moments, was simply absent. This raises a question that Augustine would have recognized immediately. If time is partly or wholly a product of conscious experience, what happens to time when consciousness is absent? Does the physical time of clocks and planets continue independently of any experiencing mind? Most physicists would say yes. But the question of how physical time and experienced time relate to each other remains one of the most interesting and unresolved questions at the intersection of neuroscience, philosophy, and physics. The experience of time is also shaped profoundly by emotion, memory, and expectation in ways that go beyond simple duration estimation. Boredom, for example, makes time feel slow, not just because we are paying more attention to its passage, but because we are in a state of wanting time to move faster than it is. The mismatch between desired and actual pace of events creates a felt resistance, a sense of time dragging. Anticipation does something similar. Waiting for something you want to happen, something you are looking forward to, tends to make time feel slower. The mind reaches ahead toward the anticipated event, and the gap between now and then feels stretched. Dread works similarly, except that the emotion attached to the anticipated event is negative. Time moves slowly towards something you do not want, and grief can do something very strange to time. People who have lost someone they loved often report that time feels both frozen and rushing simultaneously. The present moment feels suspended, as if time has stopped, and yet the days and weeks pass anyway, the world moving forward with what can feel like cruel indifference. Grief reveals the degree to which our experience of time is entangled with meaning, with relationship, with the presence or absence of the people and things that anchor us in our lives. All of this research and reflection on the perception of time points toward a conclusion that is both humbling and fascinating. The time we experience, the felt duration of moments, the sense of the present moving forward, the memories of the past, and anticipations of the future, is not a simple readout of physical time. It is a rich, complex, constructed experience that depends on the state of the brain, the content of consciousness, the emotional tone of experience, the density of memory, and a great many other factors. Physical time and experienced time are related, but they are not the same thing. And the gap between them, the space between what clocks measure and what we feel, is not empty. It is filled with everything that makes us human, with attention and emotion, with memory and anticipation, with the particular texture of being a conscious creature moving through a universe it did not make and does not fully understand. Which brings us, at last, to the question that this entire journey has been building toward. Given everything we have explored, given the flexibility of relativistic time, the directionality of thermodynamic time, the possible timelessness of quantum gravity, the constructed nature of perceived time, what can we say about whether time actually exists? Chapter 10. Does time exist? We have traveled a long way to arrive at this question. We began with the simple, familiar experience of time passing, the sense that moments flow from past to future, that yesterday is gone and tomorrow is coming. We followed that experience through ancient philosophy, through Newton's absolute time, through Einstein's flexible space-time, through the thermodynamic arrow, through the block universe debate, through quantum mechanics, and through the neuroscience of how the brain constructs the feeling of duration. And now we arrive at the question that has been waiting underneath all of it. Does time actually exist? It is worth being careful about what this question is asking, because it can mean several different things depending on how you approach it. It might mean, is time a fundamental feature of the universe, built into the deepest level of reality? Or it might mean, is time real in any sense at all? Or is it purely an illusion? Or it might mean something in between. Is time something that exists at some levels of description, but not others? Something that emerges rather than something that is foundational? These are different questions, and they have different answers. Let us work through them one at a time. The first question is whether time is fundamental. Here, the evidence from modern physics is genuinely surprising. As we saw in the chapter on quantum mechanics, the Wheeler-DeWitt equation, which describes the quantum state of the universe, contains no time variable. The universe at its deepest quantum gravitational level appears to be described by a static, timeless equation. Time does not appear as a fundamental ingredient in the most complete description we currently have of the universe as a whole. This does not mean that time is an illusion. It means that time may be emergent, arising from the structure of the timeless quantum state, rather than being built in from the start. The physicist Carlo Rovelli has developed this idea extensively in his work on loop quantum gravity. In Rovelli's picture, the fundamental description of reality contains no time. What we call time emerges from the relational structure of the quantum world, from the correlations between physical systems, from the thermodynamic arrow that distinguishes past from future. Rovelli argues that we should not be disturbed by this conclusion. Many things that seem fundamental turn out to be emergent. Temperature is not a fundamental property of reality. It emerges from the motion of atoms. Smoothness is not a fundamental property of surfaces. It emerges from the arrangement of molecules. Perhaps time is similar. Perhaps what we call time is the macroscopic face of something that looks very different at the fundamental level. Something that does not resemble our everyday experience of moments flowing from past to future. The physicist Lee Smolin takes a very different view. In his book Time Reborn, Smolin argues that time is the most fundamental thing in the universe, more fundamental than space, more fundamental than the laws of physics themselves. In Smolin's picture, the laws of physics are not timeless truths that govern the universe from outside. They are themselves evolving, changing over time, products of the universe's history, rather than fixed constraints imposed upon it. Time, for Smolin, is not something to be explained away or reduced. It is the ground of everything. Between Rovelli and Smolin, between the timeless and the time-first views, there is a genuine and unresolved scientific and philosophical disagreement. Both positions are held by serious, technically accomplished physicists. Both are supported by detailed theoretical arguments. Neither has been confirmed by experiment in a way that decisively settles the question. What about the second question? Whether time is real at all, or purely an illusion? Here, the answer is more straightforward, though it requires some care. The idea that time is simply an illusion, that it does not exist in any meaningful sense, is hard to defend and easy to misunderstand. When physicists say that time may not be fundamental, they do not mean that clocks do not tick, that processes do not unfold, that events do not occur in sequence. All of those things are real. Your heart beats, flowers bloom and wither, stars form and explode. These processes are real, and their sequential character is real. The question is not whether these things happen, but what kind of thing time is at the deepest level of description. To say that time might be emergent is not to say it is illusory, any more than saying temperature is emergent means that heat is an illusion. You can genuinely burn your hand on a hot stove. The heat is real. It is just not fundamental in the way that the motion of individual atoms is fundamental. Emergent phenomena are real. They just arise from something deeper. So in the sense of being a genuine feature of our experience and of the physical world at the scales we inhabit, time is absolutely real. The question of whether it is fundamental is a separate question, and the honest answer is that we do not yet know. The philosopher Julian Barber has developed one of the most radical and carefully argued versions of the view that time does not exist at a fundamental level. In his book, The End of Time, Barber argues that reality consists of a vast collection of what he calls nows, instantaneous configurations of the universe. Each now is a complete static snapshot of everything that exists. There is no movement from one now to the next. There is no flow. Each now simply is, complete in itself. What we call time, in Barber's picture, is the pattern of relationships between these nows. Our sense of time passing, of moving from one moment to the next arises from the fact that each now contains records and memories of other nows. We experience time because each instantaneous configuration of the universe contains, encoded within it, traces of other configurations that we interpret as the past. We are, in a sense, time capsules, each of us a now that contains the memory of being many previous nows. Barber's picture is strange and difficult to fully accept intuitively, but it is mathematically serious and philosophically rigorous, and it resonates with the timeless character of the Wheeler-DeWitt equation in quantum gravity. If the fundamental description of the universe is timeless, then Barber's vision of a universe of static nows may be closer to the truth than our intuitive picture of flowing time. The philosopher of physics David Albert has argued for a different approach. Albert suggests that what needs explaining is not time itself, but the arrow of time, the direction from past to future. If we can explain why the universe has a low entropy past and a high entropy future, why processes run in one direction rather than the other, then we have explained most of what needs explaining about time. The fundamental existence of time as a dimension of the universe, Albert is willing to take as given. What requires explanation is its directionality. This brings us to a third way of understanding the question of whether time exists, which is to ask whether our everyday concept of time, the intuitive picture of a flowing present moving from past to future, accurately describes reality. And here the answer from physics is fairly clear. It does not, at least not completely. The flowing present, the sense of a universal now advancing through the universe, is not supported by the physics of relativity. As Einstein showed, simultaneity is relative. There is no universal present. Different observers have different nows. The present moment is not a global fact about the universe, but a local feature of each observer's world line through spacetime. The block universe picture, in which past, present, and future all exist equally in a four-dimensional spacetime, is more consistent with relativity than the flowing time picture. But as we saw, the block universe has its own difficulties, including the challenge of explaining why the present feels special, why we experience time as moving rather than static. What emerges from all of this is a picture that is genuinely complex and genuinely uncertain. Time is real in the sense that temporal processes, sequences of events, the difference between before and after, are real features of the world we inhabit. Time may not be fundamental, in the sense that it may emerge from a deeper timeless description of reality. Our intuitive picture of flowing time is not fully accurate, in the sense that there is no universal present, and time is far more flexible and observer-dependent than our everyday experience suggests. And the experience of time, rich and vivid as it is a construction of the brain, rather than a direct perception of physical time. None of this means that time does not matter. It matters enormously. Every process we know of, every life, every thought, every interaction, unfolds in time. Time is the medium in which everything happens. Even if it turns out to be emergent rather than fundamental, that emergence is one of the most remarkable features of the universe. A macroscopic structure that makes possible everything we value and everything we are. There is something quietly wonderful about the fact that we can ask this question at all, that the universe produced, after 14 billion years of expansion and cooling and structure formation, creatures capable of wondering about the nature of the medium in which they exist. We are patterns in time, asking what time is. We are processes, asking about the nature of process. We are temporary configurations of matter and energy, persisting long enough and becoming complex enough to reflect on what it means to persist. Time may be fundamental or emergent. It may flow, or it may simply be. It may have begun at the Big Bang, or it may extend beyond our observable universe in directions we cannot access. It may be built into the deepest structure of reality, or it may arise from something deeper still. These questions remain open, genuinely and beautifully open, at the frontier of human understanding. What we can say, with some confidence, is this: time is not what it first appears to be. The simple, obvious, familiar thing that you have been moving through your entire life turns out, on close examination, to be one of the most subtle, complex, and mysterious features of the universe. And the fact that it feels so ordinary, so taken for granted, so woven into every moment of existence, makes that mystery all the more remarkable. You have been inside time your whole life. You have never been anywhere else. And yet, after everything we have explored tonight, the question of what time truly is remains one of the most open and inviting questions that science and philosophy have ever asked. Perhaps that is exactly where it should rest. Not as a problem to be solved and set aside, but as a question to carry with you, to return to in quiet moments, to let settle gently into the background of your awareness as the night deepens and the mind grows still. Time is passing, even now, whatever that means.